All right, you should be getting audio now. Let me know if you do. Anyway, excellent. Sorry. OBS trolling me really hard today. Yeah, I have no idea what happened. I haven't changed anything. It just decided to go bonkers and forget my video and my audio inputs. So that was fun. Okay, so today we're going to generate x86 assembly from our language that has vectors slash struct slash tuples. So if you haven't been here before, welcome, Xavier. Nice to see you, and thank you for joining me from Brazil. So we are working through this book. It is called Essentials of Compilation, and I have it up here on my shelf. I'll grab it real quick. So if you have not seen this book already, this is what we're working through. And we are using, rather than Racket, which is a Lisp, we are using Gleam, which is a strongly typed language for the Erlang virtual machine and also compiles to JavaScript. And it is a fantastic language, simple, straightforward, easy to understand, but also pretty powerful. We are about to start section 6.6, which is about, it is a pass in this compiler called select instructions, and it's explicitly translating an intermediate representation that resembles something like C into an x86 assembly that contains variables. Ultimately, we will go down to something that contains no variables, and that's the pass that is typically called register allocation. But for now, we have variables which could be stand-ins for registers or for the stack. Oh, good. So we are. You watched the first one. You got chapters 1 and 2, which are pretty simple. We are well beyond that. Welcome to the stream. I'm really glad you came. Thank you. Okay. So if you want to follow along, I'm going to switch to this, and my audio is still working. My video is still working. Excellent. This is the repository I'm working from on GitHub. I push to it basically every stream. So, okay. I do not have the amazing tiling window manager thing that Chris has, so if you see me futzing with windows, just be aware it's going to be a little bit tedious. Okay, so last time what we did was we have this program. It's in this little bit of string text here, which creates a vector or tuple that contains another tuple that contains the integer 42, and then we use vector ref, which extracts a field from that vector and does that twice. So essentially, as so many programs in this book have, the output of our program is 42. Oh, good. So this will be completely in your wheelhouse, Xavier. I'm glad to hear that. Okay, so we've got this. This is the AST that we expect to be output from this test, and I believe last time what we did was we made a compromise that if we can explain all of the output of this phase, what it's doing and what its intent is, that it was sufficient, and we didn't have to create it de novo. We just let it output what this is and verified that it makes sense. I don't really care to do that, but for the sake of catching regressions and so forth, this is fine, as long as I am comfortable and we all are comfortable with what the output of that is. Again, it doesn't exactly match what they have in the textbook, but there are some aspects of their output which seem to imply other things are going on that weren't explicitly talked about in the text. So I may send that feedback to the author. He's been on the stream a couple times, which you, Xavier, if you catch up, there are dozens of episodes at this point. But if you do catch up, you may see him on the stream on occasion. Okay, so here we are in the book. We're in 6.6. So in this pass, we generate x86 code for most of the new operations that are needed to compile tuples. We can allocate, collect, so forth, accessing tuple elements, and the is comparison. The is going to be interesting. I don't actually know what that is. Okay, so we compile global variable to global. The latter has different concrete syntax. Okay, so they're just saying that we're generating a new x86 intermediate form. And so I think that what we need to do is, what did we do last time in select instructions? What was our target? Our target was x86 var if. So we're going to duplicate that, and we're going to call it x86 global, as they do. And yeah, compile. Okay. So the essential things that are new, aside from calling into the garbage collector, into the allocator, is to dereference or set things in variables that have been defined to be vectors. So here they're talking about the read and write forms translate into move queue instructions. And remember that these are tagged tuples. So the tag contains what is the length of the tuple, and also what's the other thing in there? We'll go back to that in a bit. I forget exactly, but we have a 64-bit tag at the front of the tuple, and then so this vector ref is going to have to go, 1 plus the number of the field past the so we get past the tag. Okay, so if we're doing vector ref and we have a tuple and we want to get field n, so they're saying move q. I don't know what the 2 prime is there. But basically this variable, so to speak, is going to be a pointer. So it's saying move the pointer into R11, which is interesting. They're picking a register. And then whatever the target of the left-hand side of this is, basically do your pointer arithmetic off of R11 and move that into left-hand side. Okay, and for the vector set, not too different. We'll move the tuple into R11, and then this is the value that's going to go into this field. So it's going to be, move the whatever this refers to into the 8n plus 1 of R11. So again, this parenthesis syntax in x86 assembly is dereferencing the value. So it's like treat this as an address and then add this many bytes to it. Okay, and then so this move 0 into left hand side, because even if you don't make use of this returns the void value. It gets assigned to something in this intermediate language. So we have to move 0, the constant 0, into that variable. Okay, so they're saying these are obtained by translating from ctup to x86. The move of tup prime to register R11 ensures that the offset expression contains a register operand. So they're saying you don't want to be trying to do an offset on something that's on the stack, or an offset of a constant. It needs to be in a register. So this means R11 cannot be allocated in our register allocation phase, right? They say, why not use REX instead of R11? REX is often used for return values. But they're saying here there's a possibility that you could, you know, collide RAX. So they arbitrarily picked R11. And then, you know, patch instructions would basically do something that's nonsensical. The vector length operation should be translated into a sequence of instructions that read the tag of the tuple and extract the 6 bits that represent the tuple length, which are the bits starting at index 1 and going up to bit 6. Right. And so now remember, so the least significant bit is a tag about whether it's been copied or not in the copying collector. And then the next 6 bits are the length of the tuple. And then I forget what the other, there's like 50 bits or something up at the top, and then there's some unused at the very top. I don't remember what those are. We'll have to go back in the chapter. Okay, so allocate compiles to operations on free pointer, because free pointer is a global, right? In C or Rust parlance, it'd be like a static, a mutable static. Okay, so this approach is called inline allocation because it implements allocation without a function call. And now the reason we can do this is because we've already checked. We don't have a global heap. We have a statically sized heap right now. And so we've already checked that there's space when we get to the allocate call, so we can just increment the pointer, and that's what they're suggesting we do here. More efficient than calling a function, right? The address in the free pointer is the next free address in the from space, so we copy it to R11, and then move it forward by enough space for the tuple being allocated. Right. So copying it to R11 says now we're initializing this tuple, so it gets the head of that free space, right? And then you move the value in free pointer by the amount of what that size of the tuple should be. Okay, and then you initialize the tag and copy the address in R11 to the left hand side. So, okay, let's look at figure 6.8 in a second. Yeah, so this is where we were looking at before. Okay, this is a ways back, but that's fine. So if this is forwarding, this has to do with the copying collector. Then the vector length is 6 bits, which they're saying is, you know, obviously that allows 64, but they're only using 50. And this, okay, so this is saying, is the field in that spot a pointer or not? So if that contains a vector, then that, you know, say if field 0 contains a vector, then that bit that's part of the pointer mask will be 1. If it doesn't, if it contains a concrete, like an immediate value, then it's going to be 0. Okay, so can we go back? I'm going to have to jump. 6.6. Okay. Just to clean my mind, the language implemented has automatic memory management is compiled to natives of the GCs in the runtime. Yes. The GC is it's a 2-space copying garbage collector, and it is implemented in a C file that gets linked in. Yes. Interestingly, never in this whole series have I actually linked into a running program. Partly because I'm running on an ARM chip on this. Like I've got an Apple M1, right? But we're compiling to x86 64 assembly. So, you know, eventually I'll get that and I'll find the whole thing's wrong and I'll have to go fix some deep assembly bugs. But for now, this is more about learning. So I'm not horribly concerned with this thing actually works when you link it together. But yes, the materials, it's worth pointing out, IU compiler course. All of them are here, and there's the public student support code. And we've looked at this before, and I do want to dig into it at some point, but this runtime.c has all the implementation of the garbage collector. So if we go collect, we can look at what it does here. Okay, and they've got debug stuff in here, but basically we're giving it you know, the root stack pointer, and so the way that this is going to be implemented in the runtime is, rather than having the roots of the garbage collected items beyond the stack, they're in a separate space, separate memory space, and so we can treat that as a different stack rather than it being the call stack. It ends up being a little bit easier to determine the lifetime of things and not have random stuff get clobbered on the stack and copying on the call stack into the receiver and or the caller and so forth. So it's a separate memory space. Anyway, okay, so let's get started on this. I do encourage you, Xavier, if you want to read the C code about what's going on in the collector, go to this file. One thing it's not clear to me is whether this is actually fully operational battle station, so to speak, or whether the assumption is this is the outline and there's some specific things that the student is supposed to fill in. Because remember, this book is used as an instruction, like textbook, for Indiana University in Indiana, the United States. So this may contain holes in it that you're supposed to fill in. But yeah, there's discussion about the Cheney algorithm and so forth. Okay, so we're going to go back to here. We've created this new intermediate language. I think we need to add some things to it. Here. Actually, we might not. It might not need anything new, except that we need to restore this deref. So now that we are using R11 at this point, we need to make sure that we can generate those arguments to instructions. Yeah, so here, that's the deref, like label, I'm sorry, what is that? Label RAP. Oh. Essentially stands for the address of the free pointer global. Uses special instructor pointer relative addressing mode. Okay, we need to read this. Let's go back. Okay, the address in the free pointer is the next free address in the from space. So we copy it into R11 and then move it forward by enough space for the tuple being allocated, right? Which is 8 and length plus 1 bytes, because we need each element, because each element is 8 bytes and we use 8 bytes for the tag. And we initialize the tag and finally copy the address in R11 to the left-hand side. Okay. Refer to 6.8 to see how the tag is organized. We did that. We recommend using the racket operations bitwise. I guess that's signed or, bitwise signed or, and arithmetic shift to compute the tag during compilation. Right, so we should be doing some, oh, this will be fun. We'll need to generate some bytes, basically. The type annotation in the allocate form is used to determine the pointer mask, the type annotation, the pointer mask region of the tag, right? So if we look at, for example, explicate control, no. We still have the types in here. So when we do this allocate operation, we have the size here, but we also have the type, which is determined way at the AST of the language that the user writes in, right? So we can look at this type and go, you know, what are the types inside this vector? And for each one of those, we can say, okay, well, the first element is an immediate, an integer t. Say if the next one was a vector, like this. So the first one is a vector here, so that would get 1 in that byte, and so forth. Okay. Right, so we'll need to do something else. And I think that we'll have to look at the Gleam standard library, possibly, for what to do here. The other thing is we could actually use bit strings. That might be interesting, and that might be a straightforward way to do that computation. In the end, it turns into a number, right? Like a 64-bit number. So after we've got the 64 bits that we need populated, we can extract that from the bit field potentially, and then put it into the spot where it belongs. Okay. So now we're seeing, right, the pointer mask. The addressing mode label RIP essentially stands for the address of the free pointer global variable. Okay. In particular, the assembler computes the difference, or the distance d, between the address of free pointer and where the RIP would be at that moment, and then changes, so this is the assembler, not us, and then changes the free pointer RIP argument to some label RIP, which at runtime will compute the address of free pointer. Okay, this is something I did not know about. Really kind of wonky thing. It makes me wonder what happens at the link stage. Like what kind of business goes on there? Because who knows where that code is going to be placed, and the linker might rearrange things. Weird. Okay, so we'll need arg. We need to go back up in here in our x86 language. So we have this plain dref, which we're going to use for the vector, access operations. But we also, right, so that was this. We just never used it, and so we had it commented out. But now we're going to need it, so we need to put it back in there. But there's also this, and I think that maybe we call it instruction pointer relative addressing. Like, what we call this, like global. Let's just put it down here, global. And then we just say name string. Like, this is just like that global value thing that's in the higher level language. So I feel like it should go, we should call it this. It's not the same as this global label, which is the entry point of our program, right? And it's kind of like a dref. I think we just need to remember that when we compile this, it turns into this. So I'm going to put a comment in here, which is I'm going to call it name %RIP, and that way we remember that that's what that means. And this one is offset register, right? Okay, and I'm just going to go ahead and put value register is %reg, var is just var, and we say that gets replaced later in register allocation. Okay. Okay, so this is the allocate form. It turns into move the free pointer into R11. Increment the free pointer such that it now we've consumed the space for the vector. Whatever we computed the tag to be, move it into the 0 offset of R11. Makes sense. This first slot, first 64 bits, and then move R11, which is a pointer, into the left-hand side. So this is actually a pointer. Okay. The collect form is compiled to a call, right? So this is the arguments to collect are the top of the root stack, the number of bytes that need to be allocated. We use another dedicated register R15, so I guess we're going to take that out of consideration in register allocation. To store the pointer to the top of the root stack, again, not available. Okay, so moving R15 into RDI, which is the first argument, and then this is the number of bytes, so RSI being the second argument, and then calling collect. Okay. Okay, concrete and abstract. So here's the abstract syntax. Okay, so this is what I've just added, global label. And let me rename this to label, just for consistency with the book. Okay. Oops, I did not mean to do that. Oh, 615. Okay, so that's the thing that we were looking at last time, which is like, what does this turn into in assembly? Oh, and that's just on the next page. Okay, so I think we have enough in here to go ahead and implement the pass. So let's go into select instructions, and we need to do this this dance of changing all of our aliases and then finding all the places where we don't cover all of the all the variants. So C loop needs to be C toop, L while needs to be L toop, and this needs to be X global. Okay, now there we go, all that fun. Okay. So let's see, select statement, select tail. Okay, so let's go in here and let's add our missing patterns. So we have a sign, right? So we need to deal with these new things. And that's basically what they were talking about here. So allocate. We're going to need a helper function to get us the tag. So let's look at what we were talking about down here with allocate. And maybe I'll just, since we're going to be kind of doing some copy translation stuff here, so we're going to do move Q, and this is going to be x86 dot, this is an arg, so we need global, and this is going to be free pointer. And this is going to be register. R11. Yeah, so again, we are sharing this definition of what the registers are across multiple intermediate languages, so that's why there's this x86 base. Okay, so we start with that, and then the length goes into here, so we're going to do add q, and that's going to be x86 dref. I'm sorry. No, that's 8 times length plus 1, so that's going to be immediate. Okay. Remember, an immediate is always an integer. And then we need to get the global bit. So we'll just copy this here. Now we need to compute the tag. So what we're going to do is we'll have something that takes the amount and the type and does the tag computation. So let's say x86 immediate. We'll call it compute tag, and we'll pass it amount and t, and we'll figure that out in a minute. And then we're going to move that to x86.dref, and the register and the amount. So that's base.r11 0. And then finally, we're going to move from I might actually, because I think in other cases we've used a bare RAX, I may actually import that bare for R11. And we'll just, so this is var is just a string. So we want to do var. Okay, so we need to implement compute tag. Hello, unknown7. I would love it if you had a real name I could call you. That would be great. So let's stub this out. So this is going to take amount, which is an int, and the type, which is going to be l.type. And that's going to return an int. To do. Okay. So we will have to do a little bit of defensive programming in this function, which is okay. I'm not really upset about that. But let's assume that that's implemented for now, and let's try to fill out the rest of this stuff. So we need to go back up here and look at vector ref and vector set. Okay, so for vector ref, we need to do, so the tuple is v. And we're going to move that into a register. Yeah, let's go ahead and go up to the top. We want to import R11 because we're going to type that a lot. So I'm going to unqualify these. The editor was helpfully selecting all of them for me, and okay. So V is an atom. Oh, okay. So there's a problem here in that yeah. to say var name, and we're going to do something like this, because I think I want to do let assert variable var name equals v. Like there's no, this is atomic, yes, that's its type, but we should never have anything this should never be anything but a variable. No, I take that back. That's not right. Well, okay, hold on. So this, yeah, this has to be a variable. Like explicate control. Remember, this is our original program, and yeah, in the original program, it looks like you can do vector ref of some other expression, but the intermediate passes, the remove complex operands and so forth, the explicate control will extract these into variables so that when you get to, you know, we're talking about 3 address code in this at this stage, right? So this is the argument to vector ref has to be variable, and if we look down here, where is the, yeah, I'm trying to figure, oh, and it collapsed something weird there. Where is it? Right, so vector ref, that's always a variable. If we find all the other places, see, it's a variable there. So if we find all the places where it says vector ref, okay, it's only those 2 places. It's always a variable at this point. So we should have this invariant in our compiler. What if assigning to a member of a variable or something returned by fun? No, like the thing is, the passes that happened before this will have extracted that into sequential code that creates a temporary variable to assign the value to, and then puts that into the argument, because the arguments have to be atomic. So if I go to the type, just to be clear, I go to the type definition, this atomic is either int, bool, variable, or void. And it's nonsensical to have vector ref on an int or a bool or a void. So it has to be variable at this point. Okay, hopefully that clarified things. Oh, by the way, this index has to be an int. So we should also do we'll say index. We're gonna shadow that. Yeah, just complaining about it not being used. Okay. Let's say n. Let's call it n. So these, if we get to this point and we have a vector ref and we have not accomplished those things, that's a bug in the compiler. Yeah. Yes, the passes generate an anonymous variable for those cases. Yes. Because what you don't want to be dealing with is nested expressions at the point where you're trying to generate assembly, right? Like, that's a nightmare. So all the previous passes eliminate that, and they make it so that you can have your code as sequential as possible. Nothing recursive, no unpacking at this point. So yeah, it's just that there are some things where in the definition in Racket, in the description of the abstract syntax, you can have, like they create, you know, tagged entries where the thing is only this in the syntax, but with the way that the types are defined in Gleam, I can't express that without removing the wrapper on it. I can't express that this should only ever be an integer and this should only ever be a variable. And like the thing where, you know, I could go back to explicate control and say that when we're dealing with this, we're going to make this atomic. I don't if that's an explicate control or not. But regardless, we're going to make this atomic, and then I'm going to pattern match on it with a let assert and make sure it's a variable, and the same with the index. We could do that potentially, but we don't. I think it's okay here, and this let assert is just for my sanity, so I don't have to write case. Anyway, okay, so move q, and then we have a second move q. Which is going to be a deref of R11, and we're going to have 8 times n plus 1. Okay, and we move that into var. Okay, let's look at vector set. And I think that we're going to have to do, some more let asserts here. So I think that this is going to be the same. Okay. So we're going to move from variable var name. So this is basically the same. Let's just copy that, save myself some trouble. And then we do move from right-hand side, which is this value. Now this is an atomic. So I think that we need to I don't think that we have that sort of conversion in here. Oh no, we do. Haha, excellent. So we can just do select ATM there on that one. So we can say select ATM on value because we know that value is atomic. And then we're going to say here's another deref of R11 and our friend 8 times n plus 1. And then we will into var. Okay, so we got vector set, we've got vector ref. Okay, vector length should be translated into a sequence of instructions that read the tag of the tuple and extract the 6 bits that represent the tuple length. So they're not giving us an example here. We need to figure this one out. That's okay. What we can do, let's do this, because we know we're going to use that again. Extract the 6 bits that represent the tuple length. And Q and Shift RQ can be used to accomplish this. Okay, so we know that we're going to have to do this again, because what we want is to get the tag. So our next step will be move Q from deref R11 0, and we need to move that. I think that in this case it's probably reasonable to choose RAX. And then we can do, I guess we need to add these instructions. I don't think that they're in here. Shift right. So do we have and q? No, and q. And that would be it's just going to be an arg and an arg. We'll need to look at the reference to make sure we're constructing those correctly. So SARQ is going to be an arg and an arg as well. Okay, so we want to shift right, and that's going to be, we want to shift right 1 bit. And we're going to do that to RAX. And then we want to do and Q. And this is actually going to be pretty simple. So 63. Because we have 6 bits. You know, I could say this is like 2 to the 6 minus 1. But we can do that in our head. 2, 4, 8, 16. Did I do that wrong? No, 32, 64. So this isn't actually that bad. Okay, and then we're finally going to move that value into the variable here. So it always messes me up in the head that x86's like destination is always second. It's like inverted from how most programming languages are. Okay, so we have let's walk through this. So we're taking the tuple, which is v. It's in this variable. We're moving its pointer into R11. We're dereffing R11. So we're looking at what is at R11 slot 0. So first 8 bytes. Move that into REX. Okay, and then we're going to shift right so that we drop the least significant bit. And then we're going to AND that with 63 so that we get only those bottom 6 bits. And then that is the length. Okay. You know, there's a bit here where if you wanted to be clever and you knew the type and you had propagated the type, you could eliminate these vector length things at an earlier phase. We're not doing that, but that might require some data flow analysis that I think that they don't want to introduce right now. So okay. So it's interesting here that so we need to do collect and this vector set statement, which is just this, but not assigning anything. So I think let's go ahead and do this one. And we'll just copy it. And we just don't have a variable. So because the result of that expression, that statement is dropped. Okay, so I actually want to put that next to its twin. So we only have 2 more cases to cover, which is assign the value of this global variable to this other variable. And what is interesting to me is I don't know if we're generating code that looks like that. So we should look at the explicate control test, because this should only happen in statements that call into the garbage collector or check whether to garbage collect. So I don't know that I guess we'll find out whether that needs to be handled or not. We could, similar to our let asserts here, we could introduce a panic and say, hey, we generated bad code. You should not be doing this. But I'm not certain if that's the appropriate thing. But let's go ahead and do collect, and then we'll go back and we'll look at what we're producing in the previous phase and see if that makes sense to handle. Again, sometimes there's these little holes where like Racket is not going to care, but Gleam definitely cares because we defined a type in a particular way, therefore we have to handle all the cases. Rust would do this to us too. So, okay, the collect form is compiled to call to the collect function in the runtime. Okay, so let's go ahead and do that. So this is pretty easy. Move queue, register, and I guess we're only going to type this once, but so we've reserved R15. Okay, I see. Well, we have, yeah, RDI. Okay, and then we move Q. This is the number of bytes. I actually wonder whether we do length plus 1. I think we're doing the correct thing. Yeah. And then call Q. And here, this is actually, so this is collect, and we have to put the arity in here. So this is 2 arguments. Okay, so we've got collect. All right, let's, like I mentioned before, there's this form, assign global value. So one of those 2 statically defined pointers into a variable. So let's see if we're ever doing that. So let's see, global value. And we are, so we need to handle that. Yeah, we're doing that in multiple places. Okay. So one thing, did we do that right? Where was that free pointer thing we did? Oh, right. Yeah, that's there. Okay, so we're going to do something similar here. So this is going to be global, and this is, we'll call this gvar, global variable, into var. Okay, that one is actually really simple. Not a big deal there. It's just that this is using that instruction pointer relative addressing. Okay, so we've got statement. We need to handle tail. So tail is basically a statement plus return. So yeah, note here, by the way, we had invalid if statement. Like if we're generating anything that doesn't have a goto in it in the branches, then we have a problem in our program. And like here, if we have a return of a comparison or return of not, then we've got a problem where our program doesn't return the right type. We're only allowed to return integers at this point. Okay. I imagine that we handled an issue with, like, if we have a return, I mean, it wouldn't type check, but all right, let's go down here and add the missing patterns. Okay. So some of these might be like, yeah, we're not going to allow that. So I think that what we can do is let's get the ones that are obviously not correct down at the bottom. So global value, that's a pointer, that's an internal of the compiler with respect to generating code for tuples and garbage collection. So we should never return that. All right, so vector length is okay to return. Vector ref could be okay to return. Vector set returns void, so that should never be generated. Okay, so we're going to say panic as we'll say vector set in tail position. I'm just going to call it that. It says panic as runtime internal in tail position, and I think that we'll combine these two clauses. Let's do it like this. And we want to basically ignore all of these variables. We don't care. And we'll do the same here. Now, you know, there's no guarantee. Well, there should be a guarantee by the type checker that if our return value is vector ref, that the result of that is an integer. So I think that we can go ahead and make that assumption and then just generate the same code as we did above with the return. So a return is essentially move into REX and then jump to conclusion, right? So let's look at what we had up here in so the vector length one is interesting. Change those to brackets. Let's go up there. We need that let assert. Okay, and then we don't need to move it into REX because it's already in REX. And then we just need to jump to conclusion. Okay. Okay, and then vector ref, we need to do something similar. Let's see, vector ref, we've got, yep, let's copy this. The difference here will be that we move into, rather than to var, we move x86 register REX. And then we do jump conclusion. Okay, I just want to make sure that we are following the pattern that we did above, and yes. And I think we've covered all the cases. Now, what we will want to see is can we generate code that makes sense with variables in it? And I think that, yeah, they've got variables in this one, so we could see if our generated code kind of makes sense from that. All right. So let's go down here to our select instructions test. And we had commented it out, so we need to update all these things. Global. And we're going to uncomment that. I hope I don't get into that situation like I did last week, where it gets really upset about, yeah, it's fine so far. Okay, so I need to fix this. Remember, our order of passes has changed. So after uniquify, I think is expose allocation. Is that correct? Let's look at our explicate control test and make sure that that's correct. Here. Yeah, so I kind of want to throw these into this helper function. Right, so shrink, uniquify, expose allocation, uncover get, remove complex operands. Before, let me see, does that even work? No, wish the LSP would help me with that. Okay, we're going to make a function which is pre-passes, which just executes those passes. And we need to make sure that pre-passes, what it's going to take is input l.program, and it's going to output c.c program. So we need to make sure that we do, sorry, input type check program should be okay. Wait, did we? C-toop SC, thank you. Now it's correct. Okay, so maybe I want to rename this function. I don't really like that name. I just want to leave open the, oh, that didn't even work. Fun. Okay, well, we'll leave it there. I just want to make sure that we have the opportunity to do something with the raw parsed input if we want to. And here we can, but I think that we don't even really need that. And here we're doing it manually because this is older. Okay, so here we need to, all that type check program. actually, we can just do that here because we let's see if we do that anywhere else. No, we're just doing the syntax directly. Okay, let's run these tests. Make sure we didn't break anything. Okay, we did break something. We've got a type error. That's interesting. So select instruction tests, the negation test. Do I have an error in my type checker? I might. Let's go look. So it's saying expected a Boolean, it got an integer, and the expression was integer 10. So this would be in type check expression. Who types the type check? No kidding. Okay, no, it'd be in type check op. Yeah, okay, so here's the problem. Negate and not are not the same. So this should be integer t. We found a bug. Okay, not that one, this one. Okay. All right. Hooray for type checking and discovering bugs in our type checker. I may have to go inspect this later, but that should have been clearly, yes, you can only negate integers, doofus. Okay. So our tests here pass. What we need to do is write something for our tuple test. So what do we call these? Select instructions. Okay. So we're going to do the same like what we did here. And pray. Okay, so I want to actually pull that out and go parsed. And pre-passes. Okay, so we will have done explicate control, which basically means that what we'll get here is this, right? So I think what might be useful is to look at particular blocks for particular things, because these will still let's just say P2 is select instructions of P. And see, this returns C program, so I think that we can do this. Yeah. No. It should return an x86 program. I'm bonehead. Yeah, so we'll say blocks and we'll ignore the interference graph because we're not using that yet. So this is a dictionary of a string to x86 blocks. So given what we know about the output of this test, so like, let me just copy, for example, block 1, and we can make, yeah, so this is block 1. I just want to be able to see it in here. We can make some assertions about what those statements should look like. Okay, so I'm going to say let assert OK, and we'll call it insters is going to be dictionary.get from blocks block 1. Say block, and that block is going to be, what does that look like? Body, live before, live after. So we only care about the body. So let's pattern match that out. Yeah, body and live before, which we're going to ignore. I just want to make sure that those variables are in there in case we need them. And for clarity. Okay, so we've got the body of this block, and we want to look at what does the allocate do. So yeah, let's just write what these we think these instructions are going to be, and let's say let's call it expected, and then our final thing down here will be body should dot equal expected, and I don't need to pipe that because we're not doing anything crazy there. I like how it reads when we pipe it, because then it feels, you know, feels a little bit more read left to right, but should dot equal body and expected is fine. By the way, should is a module in the unit testing framework, so there's nothing magical about this. It's basically like case A equals B, then return nothing, otherwise panic. Okay. So we expect, and we might be able to do this by looking at the book while we're running this, working on this test. Let's go back up here to where they're talking about this. So allocate is going to be like this. So we're going to expect move q from free pointer into register R11, and then we're going to say, so this is going to be length plus 1, so we're going to say add q, so that's going to be an immediate of 16, right? Which makes sense because when we're when we call collect, we've already computed this. So, and then we have the global again. And then we have, so what does the tag look like? This is going to be interesting. We haven't implemented, remember this is a to-do, right? We still need to implement this. But what would the tag look like? So it's not add q, it's move q. So the tag for this vector, it's a vector of t. So we expect that the bottom bit is going to be 0. Then it's going to be of length 1, right? So the next bit is going to be 1. And then we have 5 0 bits. So that's the length. I don't know if that's the correct way to... Yeah, so that is an integer. So this is what we expect the tag to be, right? Now, we're going to panic because we have a to-do in here. But that's what we expect the tag to be. And then we're going to move reg R11 again into Alex6. Okay, so we did one statement. I think that this is enough. You know, we'll get the opportunity to look at these things as well. But this would be enough to trigger that bug that we have in here. So let's go ahead and figure this out. So I want to look at Gleam's documentation. And I think we could look at the language tour. I believe that that has stuff about bit strings, bit arrays. Okay, and then we just made this easy for us. But what we need to do is I mean, this is basically Erlang bit syntax, right? So ultimately, what we want is let's do something like and then I'm going to do, we want to map across these fields and figure out which ones are our vectors. So let's say the, what did they call that in the book? They refer to it down here. Yeah. The mask. Okay, so let's call it pointer mask. and that's going to be, we're going to map over the fields. And this is, you know, this is a type. And if we have case of ft, if it's vector t, and then we actually don't care about the contents of that right now because that's done separately. Then we want to return 1. And if it's anything else, we return 0. Okay. And here, we're going to keep a to-do down here so it doesn't mess that up. So what we have here is a list of integers from least significant to most significant. So, ultimately, what I want to do something is like tag size 64 bits is whatever we've constructed, and this is going to be, you know, we have 50 bits plus 6 plus, so we have 57 bits, 64, there'll be 7 bits of 7 bits. And then we have the mask, which is going to be size 50, and then we have the amount, a size 6, and then we have 0, right? That's what I ultimately want to get. And then we return tag. And I don't know that I constructed that correctly. Yeah, and I think we need to do stuff like unsigned little for safety, because let's say unsigned little size that. No, wait. It's going to be big. Because it's big to start if you're thinking about it as a bit array. Actually, I think big is the default. Is it not? Let's look at the early bit syntax documentation. So really, like if it's just bare, it's expected to be a byte. And I always have to remind myself of how to do this. See, here they're just like, this is an IP datagram, which is going to be big endian, because that's how network packets are. So I think that that's the default. Yeah. Native uses load time. Okay, default endiness is big, default signiness is unsigned. Yeah. Okay, so I think that we're fine on this. We just need to say like how wide we wanna use those. do that. I think that's what it's complaining about. Let's, for the sake of argument, let's look at the Gleam standard library and make sure that they're it's not something in bit array that we could use directly. Yeah, not really. Okay. Yeah, I don't think that we need that, actually, any of that. Okay, so what we need to do is construct this mask. And I think that maybe rather than this map, what we do is we do a fold here, and yeah, so let's turn this into a fold. And we can look at int. So I think what I want to do is fold right. And there's a problem here. So let's just say I started with 0, right? And here are accumulators and int. What I want to do is, if it's a vector, I basically want to add 1 to it. So we'll say accumulator plus that. But then we also need to bit shift it, right? I mean, the other thing that we could do is maybe see if there's bit array. That might be the easy way to do it. That's actually a brilliant idea, almost. We might need to pad it, though. I'm kind of trying to think of, because it's fine to create bit arrays that are just single bits. The question is, what does this pad to bytes do? Let's see, is there, yeah, I bet it's at the top level. let's see if we can find it. Bit array pad to bytes. Okay, so it adds the bits on the end. I think I'm making this too hard, honestly. Let's flip this back to a map. So that gives us the mass for each of the bits. And then let's figure out how to do this. We can do it with a recursive function. What is Gleam? Gleam is a functional programming language that takes a lot of inspiration from a lot of other functional programming languages, and it is a really fun one to use. So it compiles to Erlang and to JavaScript, so you can run it on your server or as a command line program, or you can run it in your browser, and that's pretty sweet. So I think I want to I'm going to call this a dumb name, flatten mask. Okay, so what I want to do here is go, this is like an accumulator, and then the fields. So we've gotten this, but this is going to be a list of ints, and ultimately we want this return an integer, right? And heck, maybe we could do this all in one. But what I want to do is, rather than do it this way, because I need a special case where there's only one field, right? So if we have the empty list, we return accumulator. If we have one field, we'll call this bit, then we return, and so this will actually make this one irrelevant, but okay, so then if we have bit and rest, this is where we call, what we're going to do is we're going to say flatten mask, and we're going to say int.bit shift left accumulator 1 plus bit, and we'll pass rest. This is what I wanted to get to, yeah. Oh, yeah, no, this is way different from Python. Okay, so now I want to go flatten mask. So let's do mask, and then since this is a pipeline, I'll pull this out. It's actually not more complicated. I would say in some ways it's easier than Python because you have fewer. Well, let's say you don't have. You don't have objects. You have types, but you don't have objects. So you can't have state and functions coexisting. You basically work with data. So in some ways it's simpler. It has some FP patterns here, like we're actually doing self-recursive functions to process a list. Honestly, I could probably do put this into flatten masks and have this do operate over list type. But the main thing to call out here, reason why my brain was getting stuck on, can I do this with a fold or not? The problem is if you have 1, you don't want to bit shift it, right? But if you have more than 1, you want to add the current bit and then shift it so that the next one, except this isn't right, we need to list reverse, because we want the bottom bit is going to be, we want it to be least significant, so we need to do list reverse here. Or we could do it before we map. That's fine too. Yeah. How long have I been programming? Oh, you're gonna date how old I am, man. You don't understand anything about coding. So officially, I've been in the industry, I would say 20, almost 20 years. I've been programming since I was in high school, so it's probably more like 30, maybe more, but professionally almost 20 years. So, and I'm doing this for fun. So thank you for coming to my stream, by the way. Okay. So now we should have computed the tag, and honestly, I think I want to make this public so that we can write some tests for it. And I think that that would be a really valuable thing to have. And what we'll do, because our ultimate goal is to get to write out all of this. So I think I'm going to comment out this function. And let's write some tests for the tag function. Select instructions, compute tag, test. Okay, so we can construct some of these tags manually ourselves. Oh, wow, that was not what I intended to do. And then we can sort of make some pretty simple assertions on them. So let's take the case of that one where we had a single vector that contains an integer. So we know that it's basically going to be we have a 0, and I think we already did this, right? So here's our tag for that one, right? No, this is the vector t. It's still length 1 though. So what we could do is we could say that bit is going to be 0. So let's take make sure I get my parentheses lined up here. Except, yeah, okay. So let's do compute tag 1 of that, length 1, should dot equal, and then since we're using bits, okay, so that's a simple one. This one, that should have 1. Okay. Let's make another example that'll be useful. So the inner one here should equal, and this will be the same value, but without that most significant bit being 1. I've tried to learn how to program many times until I lose passion the next day or two, Lamel. You know, I don't know how to how to address that, but really I think the answer for me was always the thrill of the chase of the problem. That's why I still do these streams. You know, I'm doing something that, yeah, it's kind of instructional, but it's also for my own interest. And I love learning and thinking about problems, strategizing the solutions to those problems. And that's what keeps me going in programming. So the other thing that can help, I would say, if you're just starting out, pick something very small that you can get wins on early. Because if you are struggling with, for example, like this is not, Gleam is a great language, but like you said, you were trying with Python, stick with Python. Python is great at small programs. And you can learn a lot by just getting familiar with tackling more and more difficult problems with Python. But don't get discouraged. Like, a big part of programming is suppressing your frustration and trying to find the things that you need to understand to tackle the problem. It requires persistence. And I would say also, if you're just starting out, go for learning, not for accomplishment. Treat the learning process as the thing that you're going for. Like, hey, I learned how to do Hello World. Can I look at everything that's in that program and understand what it means? And then how can you extend that to do something different? What new concepts can you learn from that? That's where you should start, and feel less like tempted to go to, say, like Cursor or Claude and have it generate something for you, because you'll be missing out on the learning. As powerful as those tools are, don't let them get in the way of your learning. If what you want to learn to do is to program, if what you want to learn to do is do something specific that programming can get you to, then look into what you need to understand to be able to accomplish that. And yeah, it's hard. I won't lie. Yeah, pick a small project. Well, ray tracing. Oh man. Yeah, ray tracing is great, but think of all the concepts you have to know, Xavier, to get to ray tracing. Yeah, ray tracing is a cool problem, though. Okay, so I need to get more. Let's think about some other types that we can. So let's pick a vector, say like length 3, where the middle one is a vector. Let's say, let's have an integer. Let's have a vector t of a Boolean t. I know these are canned silly examples, but and let's have another integer t. Okay, so this, first of all, what am I doing there? Okay, so this, we can talk about what the contents of this should be. We know at the top we're gonna have a 0, because this last element is not a pointer. We're gonna have a 1 because this one in the middle is a pointer, and we're gonna have another 0 because this is not a pointer. And then we're gonna have 6 bits, which are the length. The length is 3, so we're gonna have 1, 2, 3, 4, and then 1, 1 in binary, which is 3, and then we're gonna have 0. Okay, so this is actually not that hard to like puzzle out in my head what this tag should look like, but computing it, man, it's harder than it looks. So let's run this test and see if we made any mistakes. Okay, so I wonder if we have an endian issue here. Which test was it? Let's comment some out. Let's comment both of those out and see if it's this first one. No, that one's correct. It's got to be our ultimate one. I bet that one's correct as well. Yep. Okay, and it's because we had these pointer masks up in here. Okay, so we got 262. Or wait, it should equal 262. We got 134. Okay, so I wish Gleam had a REPL actually. What we could do is look at the generated Erlang. That's what I'm going to reach for, because Erlang EOC. Let's see. Oh no, that's the ebin. I actually want the generated Erlang code. Here we go. No, that's cache. Ish, that's gonna be bad. Okay, here we go. So this is EOC passes select instructions test. Okay, so we're going in the deep cut here. Thank you, Chris and Xavier, for talking to our new guest about this particular thing. Okay, so I need to go down and find compute tag test. Okay, so yeah, I forgot the syntax here in Erlang for bits, for binary. Okay, so this is what we expect. That's 262. Okay. Well, what we could do is we can say, what was it producing? 134. We still have the Erlang big syntax up here, yeah. Size 64. Okay, no, that's not what I want. That's wrong. No, that's... That might actually be correct. Does that fit in 1 byte? Yeah. So we can puzzle that out, what that would be, right? Remember, we have 50 of the 64 bits for this pointer mask, and we only have 3 elements, so we're not going to exceed those first 8 bits, really. Okay, so do I have something in Erlang that will let me print this as bits? Okay, Erlang. Maybe I'll just Google it. Okay, so we'll say Erlang print number as bits. I think there might be something in here with, oh yeah, maybe in format. Oh yeah, where is that? Folks, I'm just trying to save myself the problem of, okay, so here we go. Here's the control sequences. So string syntax, float. Okay, standard syntax. Where's the numeric syntaxes? Okay, the default base is 10. So we do, right, so we can do %2b. Yeah. Not percent. $134. Okay, so what do we expect? Oh, we have too many zeros. Did I literally just type too many zeros? Or did we just do it wrong? I think there's something wrong with our algorithm. Let's do it the dumb way. I'm gonna just throw that in there and see what happens. Okay. Okay, and we're gonna narrow this such that we don't get these other ones in there. And the other thing that I need to potentially do is make sure that all right, now that I've removed those other ones, let's just see what happens. Okay, so our accumulator is 0, our fields are 0, 1, and 0. So we should get this. Hi, this is, we are writing a compiler of a Lisp-like language in the Gleam programming language. And we're following this book I showed at the beginning of the stream, Essentials of Compilation, an incremental approach in Racket. And I've got the PDF version of it up here somewhere. Yeah, so here we're And what we're doing is we are writing a step in the compiler that turns a C-like language into an assembly-like language, an x86 assembly. And part of that is when we are allocating structs, vectors, tuples, whatever you want to call them, on the heap, we need to tag them, and we tag them with a 64-bit integer that represents what the contents of that object on the heap is. So, okay, so what we're trying to figure out here is what is the mask. So in this one we expect 0, 1, 0, right? And I wish I could just turn this directly into the bits, but we have to figure out how to do it. Okay, so if we have a single bit, we just add it, right? So if there's a vector 1, that seemed to be fine. I think it's in this part. So arithmetic left bit shift. The other possibility is that we could look at what this is. So we'll say let bin equals that, and then we'll put that let assert bin, and I can put this echo bin in here and see what we're getting. Now that's actually not going to be that useful, because remember, all of our stuff fits in the bottom byte. Oh, but it shouldn't. It should look like, what do I expect here? It should look like 0, 0, 1, which would be the 262, right? 1, and then go to wait, 8. No, 6. Shoot. That's what it should look like. So it feels like this bit is not being, this bit for that middle. Yeah, because we use 7 bits for this flag, which is related to the copying or the forwarding in our garbage collector, and then we have 6 bits for the size. So we have only one more bit, and that bottom one should be, oh, is it this? What if we remove this case? Does that get us the right thing? I don't think it does, because if we have I think we need to do this. Does that overshift though? Okay. Let's think about what are the cases. So if we have if we have exactly one field, yeah, I think this is wrong. I think this is correct. If we have exactly one field, then whatever it is the mask for that field. And that's the least significant bit. So if we get, let's say we're working on this, you know, we have 0, 1, 0. We want this to become, right? So, and this is from, we're doing from last to first. So this is already reversed. This is already reversed. Or maybe I'm just thinking about this too hard. Okay, we're gonna redo a lot of this. Let's call it compute mask. And that's going to be, we're going to start with 0 and we're going to give it fields. And when I say 0, what I mean is this is not going to be what's the value, although I guess we need to keep that around as well. Yeah, we're going to do, we'll just say it's a tuple of 0, 0. Okay. Okay, so this is going to be our accumulator, and it's going to be a tuple of integers, one of which is going to be the result. And the fields is going to be a list of L.type. And what I want to return is a single integer. So I don't even need this separate function because I'm not going to special case it. I'm just going to fold. So let's not do that. I'm going to fold over fields, and the accumulator is going to be int, and then the field is going to be an L.type. Okay. Yeah, I think I was trying this too hard. So we know this needs to return, we'll say this, we want the first field to be how much we shift, and we want the last one to be the result. So we'll say mask.1. Okay, so we're going to say this is the we'll call this field count, and then we'll call it bits equals accumulator. So we want to do this pattern match again. And then we want to pipe that into int bit shift left field count. And then what we want to return is field count plus 1, and then int bitwise or of the bits with the field mask. So we're iterating through the fields, and then if this is a vector, so it's, in other words, it's a pointer to something, we want that bit to be 1. Yeah, and so we bit shift left, which should leave zeros at the bottom, I would hope. I sometimes hate this arithmetic. All right, so we got. Let's just pull this out, and we can say at the end we got 1. Oops, cancel. So we've got the field mask for this field. We're keeping track of how many we processed. Obviously, the first one gets the least significant bit. The last one in the vector gets the most significant bit of this. All right. So let us see if we get what we expect. All right. Cool. Note. Least significant byte 6. Next byte 1. And here I did it with 32 bits. We have 64. So, okay, so we got the right answer. Yay. Yeah, we're going to get rid of that. All that business. Okay, so now I need to make sure that these still work. And we probably need to make some additional ones. So let's make sure those still work. Okay, those are correct. So let's make one. Shoot. Let's make one that's like 5, and we'll put some more vectors in there at the end. Okay, so that's our type. It has 5 fields, 3 of which are vectors, so we expect the first one to be 0, the second one to be 1, the third one to be 0, and 1, 1. So that's what we should get. Okay, except that now I have 5, so I need to adjust the length here. So that's 5 would be 1 0 1 0, right? 1 plus 4. Okay. So I feel pretty good about this now. So I think that I need to wrap up for the day. Yeah. Yeah, I'm so glad that sometimes it's just like, if I were writing this in C, it would be so obvious how to do it, right? But like, hey, I'm not writing this in C. I don't have, direct access over the bits of numbers. We eventually figured it out. It's fine. Now, I think that what we want to do here is I want to be able to make sure that this bit that we've already written passes. You literally just suggested it to me. List. Okay. So I want to see, let's take the first 4 instructions from this block that we generated. We expect to be generated, and it's for this statement, right? That assignment statement. And I want to make sure that we're generating the code that we expect here. And then maybe next time we can go back and we can fill out the rest of this block and maybe do some more. So let's run this test and see what we got. And it passed. So at least we're generating the code that I would expect. We've got the correct tag. We are doing what was suggested in the book. We're going to need to do more of this. We're going to have an assignment to an empty, like basically an ignored variable, and some vector sets of things. So this will be interesting to kind of finish this up next time. So I want to quit here. I'm going to make a I'm going to commit here. And I'll push that so you all can see it. And I am considering streaming again tomorrow. So maybe what we'll do is we'll finish up the test if I feel up to it. Watch my socials, watch the YouTube channel if you want to come in and have a look at us finishing this up. The other thing I was considering doing if I stream tomorrow is I talked in previous streams about doing pretty printing of our ASTs, which I think that would be really, really good, because then we can go back and the thing I ultimately wanted to do with our little compiler explorer bit, which is down here in UI and is all of the Luster stuff, which Luster is super fun, by the way, if you haven't seen it. But what we can go back in there and do is have a drop down that lets us select a particular phase to compile to, like not go through the whole thing, go to a specific phase, and then use that AST that we get as the output of that phase to pretty print what am I trying to say? To pretty print that syntax tree into something that you can actually sort of look at as text. I think that would be super, super good. And I think I even have up here, Glam is the name of it. Giacomo Cavalieri, who's a core team member, has this, ironically, Glam, also the name of a library in Rust for doing graphical math. But in Gleam, it's about building a pretty printer. So we'll look into that potentially tomorrow if I'm filling up for it. Otherwise, we'll see you next week. thank you all for coming. New folks, I hope you learn something, or you enjoyed talking with the regulars on the stream, and thank you for coming. We'll see you next time.